18 EC63. Myself, Dr. Narayan. I have done my doctorate from the famous Indian Institute of Science, Bangalore, and I'm life member of IEEE HKN of Indian Institute of Science chapter, a senior member of IEEE, and a senior professor in Department of Electronics and Communication Engineering. I have my website and my profiles are shown. I'm also very active in the social media. You can follow me if you're interested. So this is my brief introduction, as you already know. So far we have studied what is antenna, basic antenna parameters, radiation pattern, field radiation pattern, radiation intensity, directivity, beam width, beam area. So as you know, the antenna is represented by spherical coordinate system as shown in this figure. So if any antenna is placed at the origin, if you want to find the field radiation pattern or the power radiation pattern at a distant point P from the origin, you need to find the ER, E theta and the radial components. So that is what we have understood. We have also understood what is beam solid angle. Then we have understood what is power radiation pattern. Then we have found the beam area using the approximate method and the actual method, exact method and the approximate method. In exact method, you integrate the power radiated over d omega, and in the approximate method, you multiply theta hp and phi of hp. So this is this concept will come into play when you are doing the directivity of the antenna, the concept of ds. So for d omega, it is sin theta, d theta, d phi. For the surface ds, you will get r square sin theta, d theta, d phi. So when we are doing this problems, I will explain you once again. So then we have also understood your radiation intensity. That is what I was trying to tell you here. This r square sin theta, d theta, d phi. What we are finding here, r square sin theta, d theta, d phi. This whole thing is ds. And sin theta, d theta, d phi is d omega. So r square into d omega is your ds. And power density into r square is nothing but your radiation intensity. Then we have also understood what is average radiation intensity. Then directive gain or the directivity of the antenna also we have understood, which is given by radiation intensity divided by average radiation intensity. Given radiation intensity divided by power radiated by 4 pi is nothing but your average radiation intensity. So this is what we have understood so far, and we have also done problems on antenna, beam area or solid angle. So that is what we have done so far, and in today's class we will understand what is antenna beam width. What is antenna beam width. So how does an antenna radiate power? So you have whenever an antenna radiates a power, it radiates through various lobes of the antenna known as the major lobe and the minor lobe of the antenna. So what you are seeing here is the actual three-dimensional radiation pattern of the antenna. This particular lobe, what you are seeing, is known as the major lobe. This is known as your major lobe, and this is known as your minor lobe. So most of the radiation or the most of the information which is radiated from the antenna is contained in the major lobe of the antenna, and all your minor information or the losses will be present in your minor lobe in the antenna. So whenever you are designing an antenna, the aim should be to minimize these minor lobes to as much as possible, or the area under the minor lobe should be reduced. So you can have more than one minor lobe. So this is one minor lobe. This is the second minor lobe I'm trying to draw here. So this is how you will get the radiation pattern from the antenna. Same thing in polar coordinate system. So this is your major lobe. This is your major lobe, and this is your minor lobe. This is in polar coordinates. So this is how you need to draw in polar coordinates. Now some of the terminologies which will be effectively using towards the antenna design and solving the problems are known as half power beam width or antenna beam width. This antenna beam width is also called as half power beam width. Half power beam width. This antenna beam width is also called as half power beam width, also called as half power beam width. So how do you find the half power beam width is this is your maximum point P. So when the power drops to half of its maximum value or the 3 dB point, draw a parallel line to x-axis. So wherever this intersects, that point is your half power beam width. So I'll draw one more line here, draw one more line here. Okay, so this particular intersection point, wherever we get, this is known as your half power beam width. So this beam width, when 50% it drops to the maximum value, is known as your half power beam width of the antenna. Half power beam width of the antenna. Then you have another thing which you need to understand is known as the beam width between the first nulls. So this is your minor lobe, this is your major lobe. In between these two, there is no radiation. So in between these two lobes, there is no radiation. So this area here, in between these two lobes, between the minor lobe and the major lobe, where there is an intersection point here, this is known as the point of null radiation. This is known as your point of null radiation, NULL, null. And this area is known as beam width between first nulls. This is one null and this is one more null. So between these two nulls, it is known as the beam width between the first nulls. So this is your minor lobe and this is your major lobe. So your null will be, this is a three-dimensional diagram. So this null will be in between these two. So the radiation between this area and this area, so this area and your this area, this whole thing is your BWF, beam width between first nulls. And when you have this 50% of the power, then 50% of the power drops, that particular thing is known as your half power beam width. So now we'll write the definition of the antenna. Antenna beam width. Antenna beam width or half power beam width, HP power beam width, HPBW, half power beam width. Okay. Antenna beam width or half power beam width, it is defined as the angular width in degrees between two points on a major lobe of the radiation pattern where the radiated power decreases to half of its maximum value. Antenna beam width or half power beam width is defined as the angular width in degrees between 2 points on a major lobe of the radiation pattern where the radiated power decreases to half of its maximum value. The beam width The beam width is also called as half power beam width. Half power beam width, also known as HPBW, because it is measured. All these definitions are very important for you from examination point of view. Please make a note of it, because the definition will carry 6 to 8 marks in your VTU university examination. Please remember that, because it is measured between 2 points on the major lobe. It is measured between the 2 points on the major lobe where the power is half of its maximum value, where the power is half of its maximum value, and also called as 3 dB beam width, also called as 3 dB beam width, as the reduction of the power to half of its maximum value, also called as 3 dB beam width, when the power reduces to half of its maximum value. This half power beam width is very important when designing an antenna, because your peak power is nobody is bothered. This half power beam width is what most of them are bothered, because this antenna beam width is very important when you are designing an antenna. See, please remember that you have this half power beam width wherever it is coming. That is a very important factor when you are designing an antenna, because it will tell you how much is your antenna beam width, and you will receive the signals only in your half power beam width direction. So this is some 30 degrees, suppose is your half power beam width, and this is the transmitting antenna. Suppose you are having a mobile phone. If you are beam width, or if you are in the area between that half power beam width direction, you will get a good signal. So if you are beyond this point, you won't get a good signal. Suppose you are going to some jungle, or you are going to a rural place, many times you won't get signal. That means either you are receiving antenna, that is your mobile phone what you are having, it has a microstrip patch antenna as the receiving antenna. This is outside this half power beam width area, or it is in the minor lobe, so that time your signal will be affected. So if you are receiving antenna, or your mobile phone is in this half power beam width area, there you will get very good signal. So that is what is the concept of your half power beam width. So if you are going beyond this half power beam width, you will not be getting any signal in the receiving antenna. So I have taken an example of mobile phone to explain you. If you are going beyond the half power beam width direction, you won't get any signal. So if when you are traveling, when you are traveling in train, bus, many times you would not be getting signals, or you will get a fluctuating signals, because you may be at the borderline of your half power beam width of the transmitting antenna. Which is the transmitting antenna? Your mobile transmitting towers are your transmitting antenna. Please remember that. Okay. Next. Many times The antenna radiation pattern, the antenna radiation pattern is described in terms of angular width between the first nulls, between the first nulls or the first side lobes or the first side lobes. This is called as beam width between first nulls, beam width between first nulls, or BWFN, beam width between first nulls and or BWFN. So if you are measuring the radiation pattern between the first nulls here, then it is known as BWFN. This is half power beam width. If you are measuring between the first nulls, then it is called as BWFN, beam width between the first null. So you have understood two concepts here: half power beam width, when the power drops to 50% of the maximum value, and when you are measuring the beam width at that point, so it is defined as the angular width in degrees between 2 points on the major lobe of the radiation pattern when the radiated power decreases to half of its maximum value. This is also called as half power beam width or antenna beam width, because it is measured between 2 points on the major lobe when the power is half of its maximum value, also known as the 3 dB point of the antenna. Many times the antenna radiation pattern is described angular width between the first nulls. When it is described between the first nulls, it is known as BWFN, or the beam width between the first nulls. When it is measured between the points at half of its maximum power, it is known as the half power beam width of the antenna. These two concepts are very important while designing the antenna and when you are doing the problems, and also comes as a definition in your VTU university examination questions. Please remember that. Okay, next, relationship between directivity and solid angle. So I'll just write relationship between directivity and beam solid angle. Relationship between directivity and beam solid angle. So your beam solid angle is nothing but omega A. This omega A we have found using approximate method, also exact method. Using exact methods, how do you do using exact method? You will do double integration of power density as a function of theta comma phi d omega. So theta phi varying from 0 to 2 pi and theta varying from 0 to pi. This already we have done. Also we have found omega A, your beam solid angle as theta hp into phi of hp. H plane aperture in E plane aperture, half power beam width. So this is your approximate method. We have done two problems on this already. Approximate method. Now what we'll do is we'll find directivity and relate directivity to beam area, and it is given as no derivation is needed. Directivity or the maximum directive gain. Directivity is nothing but maximum directive gain of the antenna is given by 4 pi divided by omega A, or the beam area. We know that using approximate method, Yeah, this is nothing but D is nothing but your directivity or maximum maximum directive gain of the antenna. Maximum directive gain of the antenna. So directivity, so your beam area omega A is given by half power beam width, in horizontal plane, in horizontal plane into half power beam width in vertical plane. Half power beam width in the horizontal plane into half power beam width into vertical plane. This is known as your E plane, H plane. These are more two common terms used in antenna and your communication terms. So this will be theta of HP, half power beam width in the horizontal plane into half power beam width in the vertical plane, phi of HP. So your direct, this is your approximate method. This is your found using approximate method. Already we have done problems on this. Already we have done problems on this approximate method. So directivity is given by 4 pi divided by theta of HP into phi of HP. So this is what you will relate directivity and beam area. But theta of HP into phi of HP is nothing but your beam area. 4 pi divided by beam area. Now this is in radians. We will convert into degrees. We know that we know that 1 radian is equal to 180 degrees by pi. So that will be equal to 57.295 degrees, 1 radian. So if you want to convert into the directivity, so if you want to convert the above equation into degrees, so what I will do is directivity is equal to 4 pi into 57.295 degrees whole square into this many degrees, theta of HP into phi of HP. Half power beam width in the horizontal plane into half power beam width in the vertical plane. We'll be doing problems on this, so don't get panicked by seeing this equation. We'll be doing sufficient problems to understand all these things. I hope I understood the relationship between the directivity and beam area. Next concept what we'll be understanding is known as antenna beam efficiency. Antenna beam efficiency. Antenna beam efficiency. Antenna beam efficiency. Okay. Antenna beam efficiency is used to examine. It is used to examine the qualities of transmitting and receiving antenna. Transmitting and receiving antenna. Receiving antenna. And it is a very important parameter in antenna design. So your beam efficiency is given by area under major lobe divided by total beam area. So what is your total beam area is? Yeah, so I'll try to use a different color here. Yeah. So this area under this major lobe. So this area, if you have to integrate and find out under the major lobe, this is known as phi of m. That is the area under major lobe. Now you are filing area under every this one. What is this? This is all area under minor lobe. So if you are finding the total area under major lobe and minor lobe together, this phi of m plus phi omega of m divided omega of small m is your total beam area omega a. So please remember that major lobe area plus minor lobe area. This is your minor lobe or the intermediate or the side lobes. So the major lobe area plus minor lobe area is your total beam area omega a. So that is your total beam area omega a, and the top one is nothing but only the area which is coming under the major lobe. So the major lobe area by the total beam area is known as your beam efficiency. So it can be defined as, main beam area to the total beam area. Main beam area to the total beam area is known as your antenna efficiency. Okay, next, if I call this as equation 1, we know that total beam area. Please follow along with me. If you follow the class, it will be very easy to clear the examination. Total beam area is nothing but your total beam area omega a will be nothing but your major lobe area plus the minor lobe area is your total beam area omega a. So your total beam area omega a is nothing but your major lobe area plus minor lobe area, that is your total beam area. So if I call this as equation 2, divide equation number 2 by omega a. So if you divide by omega a, what happens? This will be omega a divided by omega a both sides. This is major lobe area divided by total area plus minor lobe area. Minor lobe area I am representing by small m, area under the minor lobe I am representing by small m, and the area under the major lobe I am representing by a capital M divided by total area omega a. So this will get cancelled. You will get 1 on the left hand side. So your major lobe area by your total beam area. Major lobe area by total beam area is nothing but your beam efficiency. So this first term is known as your beam efficiency from the definition of beam efficiency. This is your beam efficiency term. This is actually your loss term, also known as your stray factor, STARY, stray factor. Okay, now what is that to understand here in this case is, if your major lobe area is very big and your minor lobe area is very small, what happens? Your stray factor will be very less. So your beam efficiency will be very high. So whenever you are designing an antenna, if you have a lot of these minor lobes, what happens is minor lobe area increases. So if the minor lobe area increases, your stray factor will increase. Therefore, it will impede the design of the antenna. It won't be an antenna will not be very efficient. If your major lobe area is very large compared to your minor lobe area, so the ratio of your major lobe and your total beam area will be approximately equal to 1. Then what happens is beam efficiency will be very high. So beam efficiency will be equaling to 1 if this your stray factor reduces to 0. So in practice, we cannot reduce the stray factor to 0. So we make sure that the major lobe area is as much as possible, so as large as possible. So try to design an antenna where stray factor is less than equal to 20%. So the major lobe area by total area, if it is 80%, and if it is 20%, 80 plus 20, it will be 1. Suppose this is I'm telling an example. If it is this is 0.8 plus 0.2, total will be 1. So if you want to increase the beam efficiency, increase the major lobe area. Suppose we make this 0.9 plus 0.1. So your beam efficiency is 90%, and that 90% is being contributed by increasing your major lobe area and reducing the stray factor, which can be reduced by reducing the area under the minor lobe. So minor lobe should be reduced as much as possible while designing the antenna. How you have to do is effective aperture of the antenna, what is the parameters which are going into the antenna, what are the materials you are using for making the antenna, what is the size of the antenna. All this is going to determine your beam efficiency, your half power beam width between first nulls. All these are design parameters of the antenna. So if I want to tell what are the design parameters of the antenna, so far what we have understood is beam area, beam efficiency, half power beam width, and beam width between the first nulls, and also your directivity and directive gain. So these are the various design parameters or basic parameters of the antenna, whatever you call. Now there is one small definition known as the front to back ratio. After that, we'll go to radiation efficiency of the antenna. So far, I hope you understood what is half power beam width between the first nulls, and the what to say, your beam efficiency of the antenna, stray factor of the antenna, total beam area under the major lobe and the minor lobe. So now what we are trying to write is front to back ratio. All these definitions are important. Front to back ratio. Front to back ratio. It is defined as it is the ratio. It is the ratio of the power radiated in the desired direction. It is the ratio of the power radiated in the desired direction to the power radiated in the opposite direction. The power radiated in the desired direction to the power radiated in the opposite direction is known as your front to back ratio, and this is one of another important definitions. It will come as a part of the definitions where you need to understand, explain 3 to 4 definitions, and which would be given around 6 to 8 marks question in your VTU examination. Power radiated in the desired direction to the power radiated in the opposite direction is known as your front to back ratio of the antenna. Front to back ratio of the antenna. Okay. Next important term what we will learn right now is known as the radiation efficiency of the antenna. Radiation efficiency, radiation efficiency and power gain. And power gain of the antenna. So I can write as power radiated is nothing but efficiency into input power. Efficiency into input power. Power radiated is efficiency into input power, where P radiation is nothing but equal to power radiated, and mu R is nothing but your efficiency, also known as your radiation efficiency. Radiation efficiency, and P in is your input power. P in is your input power. Okay. Now, suppose I call this as equation 1. So your radiation efficiency is equal to power radiated by input power, P in. So what happens is, I will just recap whatever we have done so far. This is, suppose, your input source, EM input source. Just let me draw an antenna, so you will know what I'm trying to tell you. Just keep drawing with me. So this is your electromagnetic source, EM source. This is your waveguide. This is your antenna. Okay. So this is your dielectric waveguide or microwave waveguide. So from your EM source, your wave goes through your waveguide where the wave is guided. Then it goes to the antenna. So from here it is getting radiated. So this is getting radiated here. So this is your power radiated. This is your input power to the antenna. See, till here, this is the guided medium. From here, it is going to the free space. So there is going to be some loss here. So there is going to be some loss here. So that is nothing but your power loss, and this power loss happens due to the free space resistance which is offered to the flow of the electromagnetic wave into free space. This is known as your radiation efficiency. Radiation resistance. So it is nothing but a fictitious. I will tell you the definition later. It is nothing but equal to fictitious resistance when connected in series with the antenna will consume the same power as actually radiated by the antenna. So when you are connecting this radiation resistance in series with the antenna, so the problem that power is lost due to that. So your power radiated will not be equal to your input power. So your radiation efficiency. So now, so far we understood beam efficiency with respect to beam area of the antenna. Now this is with respect to the power radiated. We are trying to understand the efficiency. So beam efficiency is with respect to the area of the radiated power, and this is actual power radiated by the antenna. We are trying to understand these two efficiency. See, we know, okay, now the total power, I'll continue with the derivation. The total input power of the antenna Okay, can be written as power input is equal to power radiated plus power lost. Power radiated plus power lost. So in terms of radiation efficiency, we know that radiation efficiency is nothing but power radiated by input power P in. So if I call, okay, if I call this as here, yeah, if I substitute your input power in this equation, so radiation efficiency will be your power radiated divided by power radiated plus power lost. Okay, in terms of the RMS value of the current, in terms of RMS value of the current, so power in terms of RMS value of the current, RMS value of the current, I can write power radiated is equal to I square RMS value into radiation resistance. It has to overcome the radiation resistance. Apart from that, there are some other loss resistance. So your power lost, let me call this as some equation number 2. Equation. Radiation efficiency. We'll call this as equation 1. I'll call this as equation 1. Call this as equation 2. So your loss resistance is I square RMS value of the current into R loss resistance. So I'll substitute in equation 2. Substitute in equation number 2. So what happens to radiation efficiency is equal to, on top you will get I square RMS into radiation resistance divided by I square RMS into radiation resistance plus I square RMS into R loss resistance. So your radiation efficiency, your I square RMS, I can take it outside, I square RMS into radiation resistance divided by I square RMS. This is radiation resistance plus loss resistance. Your I square RMS will get cancelled. So you will get a radiation efficiency of the antenna is equal to radiation resistance divided by radiation resistance plus loss resistance. Radiation resistance plus loss resistance. So this is how we can define your radiation efficiency of the antenna in terms of radiation resistance and loss resistance. Radiation efficiency of the antenna in terms of radiation resistance and loss resistance is what I have defined, where radiation is equal to radiation resistance of antenna, loss is equal to loss resistance of antenna. Loss resistance of antenna. This is radiation resistance of antenna. So before ending the class, so what all we have understood today? We have understood what is antenna beam width, or also called as the half power beam width of the antenna. Half power beamwidth is defined as the angular width in degrees between the 2 points on the major lobe of the radiation pattern, where the radiated power decreases to half of its maximum value. It is also called as the half power beamwidth because it is measured between 2 points on the major lobe. Then the power drops to half of its maximum value. The other parameter which we do is the power when we are measuring between the first nulls, that is known as the beamwidth between the first nulls. Then we have understood what is the relationship between directivity and your beam area. Directivity is given by 4 pi divided by total beam area, where omega is the beam area. In case of approximate method, we will find out the beam area as theta hp into phi of hp, that is half power beam width in the horizontal plane into half power beam width in the vertical plane. So if you substitute that, you will get 4 pi divided by theta hp phi of hp. This is in radians. If you want to convert into degrees, 1 radian is 180 degree by pi, so you will get 57.295. Since there are the two components there, 57.295, it becomes square. So 4 pi into 57.295 square divided theta hp into phi of hp. Then you understood what is antenna beam efficiency. That is the major beam area divided by total beam area. Then we have understood what is major lobe and minor lobe. So minor lobe divided by total beam area is known as a stray factor, and beam efficiency is major lobe area by total beam area. Front to back ratio is the ratio of the power radiated in the desired direction to the power radiated in the opposite direction. So if you have power radiated in the opposite direction, that is not at all efficient. Then we have understood what is radiation efficiency in terms of radiation resistance of the antenna. So power radiated is radiation efficiency into the input power to the antenna, and we have understood what is the input power and the power radiated, and the power radiated depends upon the radiation resistance, that is nothing but a fictitious resistance which when connected with the series with the antenna will consume the same power as is actually radiated by the antenna. So with that, we have found the radiation efficiency. Radiation efficiency is radiation resistance plus loss resistance. So this is where I will end today's class. I hope all of you understood today's concept of beam efficiency, beam area, and the radiation resistance of the antenna and the radiation efficiency of the antenna.